Good evening, everybody, and welcome to a rather impromptu live stream of Deep Sky, Avoid the Close Encounters. We thought we would do something while we're in lockdown and bring you some Deep Sky observing. So with us tonight we have Steve Thurn, Section Director for the Astronomy for the People for the ASV. How you going, Steve? You all ready for tonight?
Certainly are.
All right, so let's bring in Stefan Nebel. And Stefan, some of you might remember from our Eclipse live stream. Stefan answered all of the questions for everybody wonderfully well. We'll bring in Jill. I just realised some of us have still got some funny names written up there from when we were testing, but that's all right. We've got Lee, who supplies us with all of our live stream equipment during our live streams. Bring Noel in, so Noel is going to have his astronomy equipment all stacked up, and I'll bring Jen in as well for the moment. Jen's staring at her phone. We have another person live stacking for us tonight as well, but that person is trying to sort some problems at the moment. When Gerald's got his things ready, we'll bring him in. But first up, we're going to kick things off with M83, and we will get anyone who's got any questions or comments about the objects that we're looking at, please pop them in the chat, and Steve and Stefan will answer those questions for you. So Stefan, Steve, either one of you would like to talk to us about M83? Tell us a little bit about it.
Yeah, sure. I guess I can say something first. So M83 is really one of the jewel galaxies of the Southern Hemisphere. It's what we call a grand design spiral galaxy. So you might be able to see on the screen if we can zoom in a little bit, but if not, you can see a little bit of a counterclockwise spiral going on. That's because this is actually a galaxy, so a collection of billions and billions of stars, and just like our own sun. And this galaxy is located around 14.5 million light years away, so very, very distant. So all of the stars that you see sort of surrounding it, those bigger bright dots, those are all stars within our own galaxy. So they're very, very close to us, essentially right in front of our eyes. Well, this spiral galaxy, the southern pinwheel, as it's called, is way, way, way off in the distance. So yeah, like I said, it's a grand design barred spiral galaxy. So galaxies come in all different shapes and sizes. Some of them are big amorphous blobs, just spheres of stars hanging around there, while others have some really intricate, beautiful spiral structure. And the spiral structure comes about because of their essentially the conservation of angular momentum as the stars are sort of all orbiting a central center of gravity in the center. And so this is the common name for this object is the Southern Pinwheel Galaxy. And this is because up in the Northern Hemisphere, up in America and Europe, they actually see a different galaxy which they've already stolen the name Pinwheel for. So obviously this is a completely different galaxy in a different region of the sky. But yeah, really, I think we lucked out. This is quite a beautiful, beautiful galaxy, and one of the brightest and closest galaxies to us, actually. Steve, do you have any interesting factoids about the Southern Pinwheel?
Well, I think the Southern Pinwheel is pretty similar to our own Milky Way galaxy. It's a similar sort of a size, so it's about 100,000 light years across, which is the current thinking for our own galaxy, and it's a barred spiral as well. So actually quite similar. You can see the bar very clearly in the picture that we're seeing from Jen's setup, and you can actually see some of the beautiful detail of the spirals. Actually, up at the top there, you can see one of the outer arms, and in fact down at the bottom as well, heading out away from the central core of the galaxy. It's really nice. Yeah, exactly that. And down at the bottom, you can see that one flying away. Just beautiful. In just through a normal telescope, you wouldn't see this amount of detail. But in a dark sky, you can certainly make it out as a face-on spiral, and you can see some of the structure as well. So through my 10 or 12-inch telescope up at our dark site at Heathcote, it's a beautiful object to look at.
Anything else to add, Stefan?
Yeah, I think, you know, galaxies themselves are really, really beautiful objects. And I think a lot of the beauty comes when you actually realize what it is you're looking at. It's easy to look at this image and sort of think, oh, it's just sort of a fuzzy blob. But really, that fuzzy blob is actually the combined light of billions of stars. In the case of the Southern Pinwheel Galaxy, it's actually about 40 billion stars. Each one of these stars is, you know, a sun, perhaps just like our own with its own planetary system. But yeah, so it's not just, you know, a fuzzy circular blob. This is a galaxy just like our own Milky Way galaxy, full of you know, billions of stars. And actually, this galaxy is a really, really active galaxy, meaning there's a lot of ongoing star formation. And one reason that we know this is because when we look at this image in color, you can see quite a lot of pink fuzzy blobs embedded within the spiral arms. And those pink fuzzy blobs are regions that are really dense in hydrogen gas. And that hydrogen gas is collapsing under its own gravity and giving birth to new, bright, young stars. Another reason that we know this is a really active star-forming galaxy is because not only do we see evidence of stellar births, but we see evidence of stellar deaths. There are, in this galaxy, observable to us, around 300 supernova remnants. And in fact, there have been 6 recorded supernovae, which are stellar explosions, the violent end of a star's life. There have been 6 recorded in this galaxy alone in the past 100 years. This is really quite remarkable. Quite a high number, indicating that, yeah, this is a really, really active stellar factory.
So we've got a couple of questions. The first one, I think Jen will actually have to answer herself because it is her question, a question for her. What telescope are you using for M83? So Jen, this one's all for you to answer. What equipment are you using?
It's a Skywatcher ED120 refractor.
What camera have you got on there?
It's an ASI 1600 mono camera.
Wonderful. There you go. So Caleb, that's the equipment that she's using. Now we have a question from Lee. This is from your wife, I'm guessing.
Oh, it is actually.
But I'll let Stefan answer this. Oh, well, Steve or Stefan.
I'll let Stefan go with this one.
Stefan answer it? Okay. How do you measure galaxy size?
Oh, that's a fantastic question. Look, there are a few different methods, a few different ways of measuring the size of really distant objects like this. One way that we can measure the distance to really distant galaxies is by measuring something called their redshift. So one principle of physics is that if an object is moving away from you, the light that's coming off it is very slightly shifted towards the red. If it's moving towards you, it's very slightly shifted towards blue. This is a phenomenon that we call redshift. This was actually discovered by Edwin Hubble back in, I think, 1930s or whenever he was around. And this was one of the observations which indicated to us that the universe is actually expanding. But anyway, so we can measure how red-shifted the light is from distant galaxies and get an estimation of how fast they're moving away from us and how quickly they're coming towards us. So this gives us an idea of their relative speed. One way to know their distance is by having a sort of a standard sort of something that you can reference their the brightness to. And one thing that we can do that with is supernovae. So when supernovae blew up, usually they give off a sort of indicative brightness, and that brightness allows us to sort of reference and say, oh, okay, it's this bright, that means it must be this far. So that's one method that we can use to measure the distance of very, very far away galaxies. And if we know the distance, we can sort of use that to extrapolate their size given their luminosity and other sort of measurements. But yeah, that's a really, really fantastic question. And it's that kind of information isn't really available for all galaxies. But given that this is a relatively close one, that's something that we can measure quite easily.
I don't think Mark knows he's muted.
No.
I am muted, sorry. We have a couple of questions there. Would a black hole be at the center of the galaxy of our Milky Way? And we can pair that question with Barbara's please explain black holes. So whichever one of you two would like to
I'll answer the first one.
So you'll answer the
almost
first one
certainly.
here. Yep.
I'll let Stefan do the second one. That's the one I was chuckling
You
at.
go for this one, and then Stefan can explain what a black hole is.
Well, it's almost the answer to this one is pretty easy. It's almost certainly there will be a black hole at the center of this galaxy, as the question says, just like our own. I think most galaxies have a black hole at the center of them, and indeed, multiple black holes across the galaxy as a whole. Go for it, Stefan. Try and answer that second one.
Look, I think if I could answer the question, what is a black hole, I would probably have a Nobel Prize by now. But look, that's a fantastic question. The best explanation that I can give is that black holes are regions of immense gravitational force. So usually there are a couple of different ways that black holes can come about. I'll give you one example which might be a bit more easy to understand, and those are stellar mass black holes. So these come about when stars much bigger than our own sun end their life. And when they come towards the end of their life, that's the point where they've run out of fuel and they can no longer keep themselves stable, essentially. And so what happens is that they start to collapse under their own gravitational force. And if a star is big enough, it will continue collapsing to an infinitesimally small point. So this is what we call a singularity, essentially, a black hole, a point of almost infinite density surrounding which its gravitational field is so large that nothing can escape, not even light, hence the name a black hole. If you want a more comprehensive explanation, I think you'd have to go to university and study a degree in astrophysics, because the greatest minds in the world are still trying to answer this question properly. But hopefully my answer gave some explanation.
This is an area that Stephen Hawking specialized in and took it to the next level, really, in our understanding of black holes. A phenomenal mind.
He was indeed. Much smarter man than I am. It's not hard to do that, though. Now, Lee, what have you got? Oh, no, Lee's is gone. Is this M83 as well?
A single 6-minute exposure from a couple of months ago, because I still have complete cloud over me at the moment. So I think that was infrared filter that's got on there. I'm just mucking around while I'm waiting for the clouds to clear, basically.
Now, Katie has asked another one, which Stefan, you can fight over this one. How is black matter and black energy created? Is it related to black holes, or is it the fabric on which the universe is immersed in?
Again, another Nobel Prize winning question, if you can answer that. Look, again, absolutely
try.
fantastic question. I think the only answer that I can really give is that dark matter and dark energy, as far as we know, aren't necessarily related to black holes. To give some brief explanation as to what these are to those in the audience who might not know, essentially, most of the mass in the universe that we can see, that we call observable mass, only accounts for about 5% of the total mass in the universe. There's this immense amount of mass that we have no idea where it comes from. It's nothing that we can see, nothing that gives off light, nothing that absorbs light. So we term it dark matter. That's what dark matter is. Dark energy, briefly, is a name given to a concept that is an attempt to explain why the universe is expanding at an accelerating rate. It seems as though there's this sort of outward push, and we don't really understand that at the moment. And one way to explain that is called dark energy. Again, whole college degrees can be written about these concepts. They're incredibly complex. I hope I gave some introductory explanation. But Steve, do you have anything else to add?
No, I think we should leave it at that at the moment. We perhaps needed to have Ross Berner on the call, who's the head of our cosmology section. Stefan, you gave a great explanation there. I'm sure Ross could have added to it as well. Unfortunately, I can't really.
Well, if that's the case, Steve, I'm going to have to put this next one to Stefan again.
Oh boy.
We're getting some good ones. So I hope I'm saying your name right, Nitin. The things that are visible outside this galaxy, like on the screen, so like M83, are they on their own? And do they not belong anywhere or to any other galaxy or cluster? And so he's also asking, do they exist in isolation? Or do they belong to something?
Yeah, so almost all the time, the answer is yes. No, they are not isolated and by themselves. Most galaxies exist in clusters of galaxies, what we call galaxy clusters. I believe actually one of the targets that we will be moving to after this is an example of this, a number of interacting galaxies in a galaxy cluster. And so our own Milky Way is another example of this. We are part of a larger cluster of galaxies called the Virgo cluster. The Virgo cluster itself is part of a larger supercluster called the Virgo supercluster. And neighboring that, there are other clusters of galaxies, all which form much, much larger sort of interacting strands that are all sort of very slightly gravitationally linked. So it's quite rare to find galaxies that are sort of isolated and not gravitationally interacting with other galaxies. Just because of how dense the universe is, it's most common to find galaxies sort of in little families, little groups.
It's a great. It's actually a really good segue question, that, because on the next image we'll be looking at a wide. Not quite where I thought we were going. I thought we were going to go to Noel's.
We will be, but Gerald's just got his live stackaroonie going. This is, as Steve was saying before we came on live, this is literally live astronomy. So Gerald has his iPad hooked up to his telescope, stacking live on his telescope, but because he can't hook it up to a computer and share the screen, he has his iPhone hooked into StreamYard with the camera facing towards his iPad so that everyone can see the images that he is stacking. So this is the ultimate live astrophotography. And this is M83 as well. And this is, I assume this is a color image by the looks of it.
Color, yeah. It's color.
Yeah. So this is live astrophotography.
Come on, Gerald, prove it. Prove it.
Put your fingers in front of the screen,
Prove it.
Gerald. Yeah.
There you go.
There you go. So there we go. So I think we might move to the next object, and the next object is Noel has got for us, and that is Markarian's chain. So
just coming back to what I was saying before, this is a wide field view of a part of the Virgo cluster, and you can see a number of galaxies in this image that Noel is showing us. The object that we were specifically going to look at or talk about, we'll talk probably about the whole of Markarian's chain, or indeed the whole of the Virgo cluster, is the, if Noel can point it out down towards the bottom there, which is M84, which is a giant lenticular galaxy. So it's a type of galaxy. Doesn't have a spiral form. It's more of a, in sort of simple terms, it's a big blob, I think we'll say. This M84, we can perhaps talk about what that designation means as we go along as well. There's such a lot to cover, really. Is a huge galaxy. It has about the equivalent of 500 billion suns in there in terms of its size. And it forms a lovely sort of pair, if you like, with the object that is just above it, which is also another very large lenticular galaxy called M86, which you can see very clearly there. You can also see a number of other spiral galaxies, edge-on spiral galaxies, either side of M84 and M86, which don't have M designations, which are Messier designations there. They only have NGC designations, New General Catalogue designations. As we move sort of further up beyond M86, the next conspicuous pair there are called the EYES galaxies. Thanks for that. And the chain, as we said, is just a small part of the Virgo supercluster. I tend to do visual observing, and one of the things I'm doing up at our dark site is something we call the Messier 100 challenge, which is where we find 100 of the 110 Messier objects which are visible from Victoria and record what we see in a book. Myself and a colleague, Linda, we've done about 60 or 70 of these, and we were just getting to the Virgo cluster. There's quite a few, I think something like 11 Messier objects, something like that anyway, in the Virgo cluster. And we've done about 3 or 4 of them, but then we were overtaken by COVID and the weather. So we've got stuck with that. But it's probably the Virgo cluster, and finding these Messier objects is probably one of the hardest challenges of doing the Messier 100 overall challenge, because the objects are set in an area of space where there aren't a lot of reference stars around. So you tend to have to do galaxy hopping rather than star hopping to find these galaxies. And Markarian's chain is one of the great ways of flowing through the area of Virgo where these galaxies are and finding the relevant Messier objects. Stefan, do you want to perhaps talk a little bit more about some of the technicalities?
Technicalities of
perhaps the M84, indeed the Virgo supercluster.
Yeah. So I guess all I can really add is that, as we were saying before, these are a group of galaxies that are part of the Virgo cluster, and all of these sort of 7 brighter galaxies that make up Markarian's chain they're all located around 50 million light years away. And the namesake, Markarian's chain, it's actually, this grouping is named after an Armenian astronomer called Benjamin Markarian. And the reason it's named after him is because he was the person who discovered that they all shared a common motion and that they were all gravitationally linked and part of this cluster. I guess one other thing that I can add is that M84, which Steve was talking about earlier, as he said, it's a really, really massive lenticular galaxy. And this is actually a perfect example of a galaxy in which we know that there is likely to be a supermassive black hole at its center. And this is because some astrophysicists were able to make measurements. They observe the spectrum, so the light that is released in the hydrogen wavelength in the center of this galaxy. And they were able to find that in a region, very, very small region, about 25 light years across, there's some gas that's moving at an incredibly high speed, around 400 kilometers per second. And this is a real dead giveaway, an indication that there must be something extremely gravitationally strong in this region, which indicates to us that it's almost certain to be a supermassive black hole. And yeah, I can't remember if you exactly discussed it, but you brought up the EYES galaxy. So NGC 4438, which is sort of in the middle there. It's the interacting galaxy. So to those in the audience who haven't heard that term before, interacting galaxy, that's really what it sounds like. It's two or more galaxies, so these huge clusters of stars that have gravitationally interacted in such a way that they fall towards each other and fall into each other. And this can, really disturb the spiral galaxy that some galaxies tend to generate. And so a lot of more globular lenticular galaxies like M84 are thought to have undergone some gravitational merger, some interaction distant in their past, which has disturbed their structure in such a way that they're just basically big amorphous blobs. But the EYES galaxies, those two interacting galaxies, are an example of interacting galaxies where we're seeing the interaction in the process. We're seeing them just crashing into each other. And if you weren't aware, this is actually going to be the fate of our own galaxy. Unfortunately, our biggest neighboring galaxy, called Andromeda, which isn't visible to us in the southern hemisphere, at least not easily. This galaxy, it gets about 10 degrees above the horizon, but it's a bit of a challenge to target, to image. But anyway, this other giant spiral galaxy, the Andromeda galaxy, is actually hurtling towards the Milky Way galaxy, our own galaxy. And in the not too distant future, in about I think 5 billion years or so, they're going to start getting closer and closer and closer and start interacting, at which point they'll undergo a merge, and then over billions of years eventually sort of agglomerate into one huge galaxy that we'll probably call Milkdromeda or something like that. And eventually it will form its own.
Stefan, a really, really important question though. Do you think we'll be out of lockdown before that happens?
Ooh.
The world might be, but Victoria won't be. So I'm going to sidetrack just a little bit, because there's a question that I've seen posted about 10 minutes ago, and unless I pop it up, we're not actually going to really cover it for a bit. And is it an 11-year-old girl named Stella who wants to know whether every star has at least one planet surrounding it?
Well, actually, I'd be surprised if you pulled that fact out of nowhere, because on average, every star has at least one planet. That means that some stars may have 0, some stars may have 8, like our own. But on average, if you pick any random star, on average, it should have at least one planet surrounding it.
Beautiful.
Good
There
question
we
and
go.
a good
Very
guess.
good question.
Good question, that one. Well
So
done.
Noel's moving to our next object, which is, I believe our next object is, it's a double star. Beta 1 Scorpii and Beta 2 Scorpii.
Well, I'm going to start off actually on Omega 1 and Omega 2, only because
Yes.
they're a
Following me.
little bit further apart, and my rig will see them a bit easier. So, so this is at the tail end of Scorpio. So I've just lined it up in my planetarium, and now
While
switch
you're
over.
doing that, we have Andy Campbell's watching this, and he's saying that he imaged from Nil a few years ago, 9 degrees above the horizon, and he had to ask people to duck every time they wandered past his telescope when he was imaging Andromeda Galaxy. Andy, if you image Andromeda from Nil again this year, I'm going to make sure I pop my head in front of your camera just for laughs. You'll probably yell at me, but that's all right. Oh, here we go. David, who is 10 years old, would like to know, do other galaxies have planets like ours?
Yes, absolutely. So, like I said before, galaxies that are outside the Milky Way are, essentially just like our own Milky Way. They're big collections of billions of stars, and on average, every one of those stars will have at least one planet. So, yeah, take a look at any galaxy, pick anyone you like, and for certain, there are billions of planets in that galaxy. Some of them might just be like Earth, might have oceans of water, and might even be forming life. And there might be, who knows, intelligent life that's streaming on YouTube and Twitch, or their alien version and looking back at us right now.
And that's it. Thank you for that, Stefan. We are actually on Twitch tonight as well. So obviously everybody is watching it on Facebook and YouTube, and we have one person watching on Twitch at the moment, but we've got to start somewhere. It's our first stream to Twitch, so okay. So Noel's got. So what's this one, Noel?
So this is Omega 1 and Omega 2 Scorpii at the tail end of the Scorpio constellation. Now, this is a double star that's visible to the naked eye. So you can go to a dark sky site and you'll be able to spot these with your eye or binoculars. They're not sort of so close that you go, oh, wow, it really looks like one. But this is a good start, I guess, as far as double stars go. And this is what they are. I'll jump to another pair now, and we'll see them a much closer. And maybe Steve, finding double stars is a bit of fun with a telescope, so he might have experience with that.
Yeah, the interesting thing with this is that it's actually not what we might call a real double star. So it's what we call an optical double. So they look pretty close to one another, whereas in fact they're not that close to one another. But the good thing is that this is a sort of a double, if you like, that you can see naked eye, and in the part of the sky that you were showing us earlier on there. I'm just looking at. I've got a couple of facts there. So the separation between the two is actually 0.25 degrees. So a quarter of a degree. So that's 15 arc minutes. So there are 15 arc minutes.
And I guess I can say some things about these stars. Where have they gone? We've lost them.
We're about 7 seconds away from having a frame. So
nice.
Well, while we're waiting for that, we have a question from Victoria, who is 8 years old, and she wants to know if tornadoes happen on other planets because she's researching tornadoes at school.
Yes, that's a fantastic question. Oh, as long as the planet has an atmosphere, it almost certainly has tornadoes. And one great example of this is the planet Mars in our own solar system. Just recently, the latest rover that was placed on Mars took a film of the little drone that it placed on Mars called Ingenuity, and in the background of the video, you can actually see a little tornado twister on Mars in the video. So yeah, absolutely. And you can look up videos of this happening on Mars. So definitely something to look into. Put it in your presentation. I think it would wow a lot of people.
Now, so, oh, you can just see those two stars there, can't you? That's
yeah.
just, yeah.
So we're having to get right in, but we can tell that there's two different stars there. So this is probably a bit more to a genuine double, for Steve's liking.
So this is beta 1 Scorpii and beta 2 Scorpii.
Yeah.
No.
Yeah.
Yeah. So we were talking before that with omega 1 and omega 2 that they were 0.25, 15 arc minutes apart. These are 13.6 arc seconds apart. And this is a real double. So these two stars are actually revolve around one another. The beta 1 Scorpii and beta 2 Scorpii is also known as Graphias, which apologies for my pronunciation, but it's apparently it's Italian for claws because it sits in the claw end of the constellation Scorpius, the scorpion, so at the head end. They look that was great before when you managed to just sort of split them apart, and they look so very close. But in fact, the two stars, it's estimated that they're 2,200 AU apart. And AU is an astronomical unit measure, and it's and 1 AU is the distance of the Earth from the Sun. So 2,200 times the distance of the Earth from the Sun, and that's actually the distance of that little gap between those two stars. So they're, in astronomical terms, they're very close to one another, but they're quite a long way apart. That's really good.
It's very, nice and crisp. When you zoom in, you can see that separation.
Yeah. The stars are, if I get my numbers right here, about 500 light years away from us here. So quite a long way away. If anyone's interested in magnitudes, the two elements, magnitude 2.6 and magnitude 4.8. So both components visible to the naked eye in a dark sky.
So here's another question. Since we've been looking at double stars, so if stars are revolving around each other, does that mean they have a gravity field?
You've got it. Yes, that's right.
Anything that's all you want to add? That's it. You've got it. You're right. No, to extrapolate a little bit.
Stefan, do you want to add more?
Yeah. I guess I can say something. So any object that has mass in this universe has its own gravitational field. That includes us. We have our own gravitational field, although our mass is very, very small, so our gravitational force is very, very small. But so if you perhaps consider the Earth and the Sun, it's true that the Earth orbits the Sun, but the Sun actually also orbits the Earth, although its orbit is very, 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 very small. The center of this, the center of the orbit of the two is actually, well within the Sun. But if you've got two almost similar stellar components, they can both orbit sort of around each other in a sort of, pendulum-like way. But, binaries aren't the only type of multi-star interaction. You can have trinary systems as well with 3 stars, although this gets very, very complicated, and the more stars, the more unstable these orbits are. But it's not uncommon to have, one really big star with a small star orbiting it. that itself is orbiting another star. So yeah, so again, to wrap it off, any object with mass in the universe has its own gravitational field. Yes.
Yeah, in the case of Beta 1 Scorpii and Beta 2 Scorpii, the two stars revolve around each other, and it takes 16,000 years for them to actually go all the way around each other, as it were.
Now, Noel, I know you've got a cluster there, but Gerald's jumped ahead, and I think we need to share his live stack that he's got going at the moment, because it's just, I can see it on my screen and it's amazing. So I know we're jumping further down the list, but I think we make hay while the sun shines, and when we've got something like this live stacking, we should share it. So I'll just pop that up. So that is the Eta Carina Nebula. Who would like to talk about that? That is live stacked. So I don't know how many images. Yeah, there you go. Fingers on the screen to prove it's live. I know these are 60-second exposures with Gerald's equipment, but I don't know how many he's got so far. So I don't know if he... three minutes worth. There you go. How's that for live streaming? That's amazing. So that is 3 minutes worth of Eta Carina stacked live from Geelong, of all places. Who'd like to have a bit of a chat about that?
Sure, I guess I can. So, as you can see, this is just 3 minutes of total exposure. So this really is a very, very bright object. In fact, Eta Carina, this great, grand Emission Nebula, is one of the biggest and brightest nebulae in the night sky. And we're quite lucky down here in Australia. Most people up north really don't get a good view of this at all. So as you can see, this is an absolutely massive region. I believe this is quite a wide field of view as well. And you can see it, this whole nebula just sort of fills the sky. And so this is what we call, so if you're not familiar, a nebula is the name that we give to sort of a region of gas and dust that's sort of just hanging there in space. And there are, so it's not a galaxy, it's within our galaxy, and really it's relatively close. It's only 8,000 light years away compared to the millions of light years away that galaxies are. And this is, a modestly sized nebula. It's around 460 light years in diameter from end to end. And so this is what we call an emission nebula. There are a few different types of nebula. There are emission nebula like this. There are absorption nebula, which block light. And there are reflection nebulae, which reflect light. So emission nebulae, like these, are emitting their own light because there are some stars embedded within them that are giving off very high energy ultraviolet radiation that are exciting the hydrogen atoms within this cloud in a way that once they're excited, they relax back down and emit radiation in the hydrogen spectrum and oxygen spectrum and sulfur spectrum. So this is a really fantastically beautiful region, and this is it's full of tiny little objects. Gerald, I'm not sure if you can zoom in on your photo.
You want to
if you're able, would you mind?
Keyhole?
Yeah, zoom in onto the keyhole. That's really the sort of
I love this. This is
breathtaking part.
Yeah, it's amazing image, but also amazing that Gerald's in his backyard in Geelong, stacking this, and he's like, "Yeah, Gerald, can you zoom in? I'll just use my fingers to zoom in, please."
Just quickly want to say, to anyone viewing in the audience who has never done astronomy or astrophotography, nowadays technology is rapidly advancing to a point where amateurs like us, just hobbyists, can buy relatively inexpensive equipment, and in our backyard, even in light polluted city locations, we can take photos of objects like this. So if you're interested, look into it and don't hesitate to reach out to any of us. We're happy to talk our mouths off about this stuff. But returning to the object itself, that sort of brown keyhole shape, which you can see his fingers are just touching, that's what we call the Keyhole Nebula. So there are a multitude of little gems hidden within this Emission Nebula. And actually, if you look just to the left of the Keyhole Nebula, you'll see a really big, bright red star. And this is my favorite star out of the trillions in our Milky Way galaxy. This one is my favorite. It's called the Homunculus Nebula, or the Eta Carina star. And this star is a massive, massive, massive star. It's around 100 solar masses. So if you took 100 of our own sun and crammed it together, that's how heavy this star is. And what's special about this star is that it's a really, really old star, and it's nearing the end of its life. It's about to go supernova. It's going to explode in one of the most violent eruptions known in the universe. Now, this could happen today. We could see it, who knows? Or it could happen in the next 10,000 years, 100,000 years. But on the cosmic time scale, this is very, very soon. And when this happens, when this star explodes, it'll be as bright as the full moon. It'll cast a shadow during the night, and you'll be able to see it during the day. So this will be a spectacular event that probably won't happen in our lifetimes, but I think if it will, it'll make us all very, very happy astrophotographers. So this star, you can't really see it in this image because of how bright it is, but if you were to take shorter exposures and had a telescope with a longer focal length, you might be able to resolve some weird shapes around this star. It sort of looks like a peanut with two lobes. It's called a bipolar nebula around this star. And that's because this star is so close to the end of its life, it's already sort of having this sort of shudders of death. It's sort of already exploding some of its outer material out. And back in 1830, I think it was, I can't exactly remember when, I didn't write it down. 1840. Yeah, there we go, 1841. It underwent an event that we called the Great Eruption. So this star really, really ramped up in its brightness, and it actually became the second brightest star in the night sky. And back then, I'm not sure if we had telescopes able to resolve what was really happening, but this star was sort of burped, I guess you can say. So it didn't go full explosion, but it definitely let off a bit of gas.
It drank a can of Coke, didn't it?
Yeah, exactly. But this wasn't an ordinary burp. In this little, great eruption, as it's called, it actually lost 30% of its mass. And that's what gives rise to this sort of peanut-shaped lobes that it has. But unfortunately, we can't see it in this photo, but there are some people out there who have taken photos of it. And NASA has generated some fantastic photos. So if you're interested in seeing this, search Homunculus Nebula. And it's one of my favorite.
NASA to the end of that. If you add NASA to the end, I just want to point out to people on the right-hand side of the screen, you can see a little countdown. It's 35, 34, little green circle filling up. That is the countdown for every 60-second exposure that's being added to this image that we're looking at. And Caleb was talking about your relatively inexpensive. And Caleb, I know you're saying that you may or may not have spent 8K on a camera recently, but going back to your relatively inexpensive, Stefan's right. I use a secondhand Mead and a phone with a $10 eBay adapter to do what I do with deep sky astronomy. So it can be relatively inexpensive, but you also can spend $8,000 on a camera if you'd like to. It just depends on what you've got, what you can get your hands on. So you can start very entry level and then push on from there into more complex equipment.
The Homunculus Nebula is visible without cameras or long exposures up at our DART site through the larger telescopes that we have there. So through the 40-inch telescope and the 25-inch telescope, you can see the Homunculus Nebula just by bringing your eye up to the eyepiece. You don't need any long exposure. It's quite a small object, so you need a night of good seeing, but it's fantastic to see, if you like, live through a telescope.
I just say, lucky I wasn't picking my nose then. Big full screen of me popped up. We don't want that. We absolutely don't want that. So we go back to our list. Noel, what have we got in our what have we got on your screen right now?
Yeah, so this is M80. So there's a couple of there's a few globular clusters around Scorpio, and so I picked a couple out. This is a smaller one. This is M80. So whether Steve or Steph has got some comments about globular clusters.
I can talk about it from a sort of viewing point of view, and then we'll talk a bit more about what a globular cluster is. So there's within the constellation Scorpius, there are two globular clusters fairly close to one another. There's this one, M80, and there's the M4, both Messier objects. And I think poor old M80 tends to get overlooked in favour of M4. M4, which we'll talk about in a little while, we'll bring it up, is much closer, much bigger. But in fact, M80 it's a beautiful globular cluster. It's a long way away. It's about 32,000 light years away, something of that order. But it's a dense globular cluster, and it contains, just in that little blob there are actually several 100,000 stars gravitationally attracted to one another. Stephen, do you want to talk about globular clusters, or do you want me to?
Yeah, of course. So globular clusters, you can sort of infer from the name, is what we give to a group of stars, a cluster of stars that sort of are all gravitationally interlinked in a sort of way that just makes them look like a glob, really. Hence the name, a globular cluster. They sort of just form this big spherical cloud where all of these stars are sort of delicately interacting through their gravitational dance. So what actually makes this globular cluster particularly special is that it's one of the most, if not, I think it is the most dense globular clusters that we know of. So I believe that there's only like 0.1 light years in between each star. So, very, very, very close these stars are, and they're all very, very strongly interacting with each other. And actually, one interesting fact about this particular globular cluster is that there have been a number of high-energy X-ray sources found in this globular cluster, and a number of these are actually from stellar mass black holes. So these smaller black holes, not quite supermassive black holes, but stellar mass black holes that are embedded within this cluster and are interacting with some of the stars and giving off very, very high energy radiation in X-ray. So globular clusters are one of the most beautiful sort of eye-catching things that you can look in the telescope. You at low power, you see them as these sort of fuzzy blobs, but when you get a high-powered eyepiece, you can really resolve some of the stars. I think one of the most beautiful things about this universe are globular clusters, and imagining what it would be like to be on a planet in orbit of a star, on a star within a globular cluster. Now, granted, these clusters are very, very chaotic. They're sort of like a swarm of bees just all sort of swarming around each other. We don't see this because they don't move very much on the human timescale, but really this is a chaotic ensemble of stars. But try and imagine what it would be like to be standing on a planet around a star in one of these globular clusters, looking up into a night sky filled with, thousands, hundreds of thousands of stars all close to you. If you weren't burnt up by the radiation, I think it would be quite a sight.
They're very ancient objects as well. A lot of them are over 12 billion years old and have probably been round the cycle of star creation, supernovas, and more star creation a couple of times already. So globular clusters, the ones that we see that are attached, if that's the right word, to the Milky Way galaxy, they don't sit within the plane of the Milky Way. They sit around the edge of the Milky Way galaxy, most of them in what's called the halo, which is the area that sort of sits around the bright core of the galaxy. So I think that the image that we've got on the screen at the moment, I think, is M4, isn't it?
Yeah, yep. So I've just brought up M4, so you can see it's not quite as dense
No,
as MAD.
yeah.
Yeah.
We've sort of gone between the two extremes, actually, of so M80 being the most dense and M4 being a very loose concentration. But it's a much bigger object to look at because it's a lot nearer to us. It's actually only about 7,000 light years away, whereas M80 was 32,000 light years away. So as I say, M80 tends to get overlooked as the poor cousin of M4 in Scorpius. They're actually quite close to one another as we see them in the sky. But no, they're very, very ancient objects. So in Scorpius, both of these globular clusters are quite close to the heart of Scorpius, which is Antares, which is the red supergiant in the middle of the constellation.
Okay, so we're going to go to another nebula now. We're going to go across to the, if I remember rightly, I better check my notes so I don't get it wrong. It's Prawn Nebula, I think it is. It is. There we go. So this is 3 2-minute images. So this is 6 minutes worth of stacking at the moment of the Prawn Nebula. So Steve, have you got some information for our viewers about the Prawn Nebula?
Not a huge amount with this one. The Prawn Nebula is about 2,500 light years away. Stefan explained this is an emission nebula, and it sits in an area of Scorpius which has some beautiful open clusters as well, and it's on the sort of the curl of the tail. But I don't have any more detail other than that. Stefan, I don't know if you have anything.
Yeah, no, this is a bit of a weird one. It's quite a beautiful nebula, but there's just really not a lot of information about it. It's not that remarkable, I guess. It's just one of these regions within our galaxy, relatively near to us, that's undergoing star formation. So it's around 6,000 light years away, so relatively close by on the cosmic scale. And I'm not sure if so. This is the image that we're seeing on the screen at the moment. This is a monochromatic image, I believe. So this is a camera that just takes photos. Yeah, so this is a camera that just takes photos in black and white, and then we take photos through different filters and can bring out the color in the end. But if you were to see this through a color camera, you would see it having a sort of faint salmonish, almost pinkish color. And this is due to the fact that most of this nebula, most of this cloud, is made up of atomic hydrogen gas. And this hydrogen, when it gets excited by really bright nearby stars and relaxes down, it emits light at a specific wavelength. And this wavelength is well within the red sort of area of the visible spectrum. So to our eyes, it looks sort of pinkish. And actually, one of the brightest stars in this image, you can see it sort of on the left, about halfway from the middle. This is a blue giant star, a really, really luminous star that's actually causing the emission in this nebula. So now here you can see on the screen a color image of this nebula, the Prawn Nebula, with that really iconic sort of pink salmon color.
Can we get Jen to jump on quickly and just explain what she's done to get this image, what this image encompasses, I guess? How many stacks, what the processing was, if she's listening to me. she's laughing. I can see her laughing. If we can get her to just jump on and tell us a little bit about this image, just so that people understand that what they were seeing, that this is the end result if you get enough data and you process it. And she's busy, so we'll keep going, Stefan. She's hiding away in the background, I can tell. She said 1 minute, so talk for a little bit longer, and then Jen will jump on and explain what she has done to get this image.
Yeah, sure. Yeah, really, there's not much more I can actually give you about this object. It's sort of a nondescript emission nebula. There are quite a few like it, but it's a sort of relatively bright object. It's good for amateurs like us. But yeah, other than that.
Is it me, or is it not very, very obviously a prawn?
No, I can't see a prawn in it. Unless it's a prawn cracker.
Two little black eyes on a prawn at the in towards the centre. Are they black eyes?
Well, I don't know. It looks like a prawn cracker to me.
Perhaps it's because it's very pink.
Yeah. So we do have a question on it. How far away is the Prawn Nebula?
This one is 6,000 light years away. So if we were to travel at the speed of light, it would take us 6,000 years to get to it. So, that's very, very, very distant, but on the cosmic scale, it's basically our next door neighbor.
Actually, now that I look at it, like if I look side on, I can kind of see a prawn in there.
Yeah, it does. You're right.
Those little eyes,
see how the tail curls around.
those little dark spots are.
Oh, you know what? I can see it for the first time in my life.
The more I can see this little prawn that's in there. I still think it doesn't really resemble a prawn to me, but or as Caleb is saying, cat's paw nebula does look like a cat's paw, and it really, really does look like a cat's paw.
Yeah.
We've got an object on Gerald's, but I want to get Jen to jump on before we move off this one to just explain, because the vast difference between what she was showing us with the live stack compared to this processed stack is they're extremes. So convince her to unmute her mic and come and talk to us. Come on, Jen. Come on. Everyone wants to know. I'll unmute her. I've unmuted her. There you go, Jen. You're unmuted. So,
Hi, guys.
what is the process with, like, how many images does this image what's in this? How many red, green, blues? Have you got any filters? Like, what did you do?
This is 4.5 hours of 5-minute subs each in hydrogen alpha and RGB.
Only 4.5 hours.
Yep.
Yeah, it's a lot of imaging.
Yeah.
So RGB, what filters?
Hydrogen alpha and RGB.
And then you stack this in, what program did you use to stack all those images
in Astro Pixel Processor.
Oh, I'm learning that one.
Yeah, I like it.
It's
very
a good program. It's actually very user friendly, that one. It's if I can use it, anyone can use it. That's for sure. And then did you process this? Did you process this in Photoshop afterwards?
No, I went through it's called Photoscape X. It's a free program. It's a bit like GIMP and Photoshop. Okay. Yeah, you can pay for the pro, but I just mainly use it for just sharpening and brightness and contrast and stuff like that.
Well, it's a beautiful image, so it sort of shows everybody that that's 4.5 hours worth compared to what we were looking before live stacked, which was about sort of 6 to 8 minutes worth.
Yeah, I can go back to the live stack if you want.
Go back to the live stack.
Now where we're up to. Where am I?
How many have we got on the live stack at the moment? You have to stop your sharing.
Okay.
Oh, no. Not like that one. Not that one. All right, we'll move to the next object. We'll go to Gerald's here. So, Gerald, what are we looking at? What are we looking at here, Gerald?
We're looking at Omega Centaurus. Yeah, it's a pretty big globular cluster. I think it's one of the biggest.
It's the biggest. Well, the biggest in our part of the universe, if you like.
Wow.
I can.
So what have we got information-wise on Omega Centauri for our viewers?
So just a couple of facts. So it's reasonably close to us. It's about 16,000 light years away. So that's relatively close to us. It's, as I said before, it's the biggest globular cluster that's attached, if that's the right word, to the Milky Way galaxy. The current thinking is that there's about 5 million stars in that globular cluster.
Well, there's a hand in there at the moment. I don't know what he's... Where'd it go, Gerald? Where'd it go?
Live. The real stuff. And current thinking is that it's probably the remaining core of a small galaxy that merged with the Milky Way quite a long time ago. So it's a fantastic object. You can actually see it naked eye it's in the constellation Centaurus, and as Omega Centauri suggests. Now it's got a star designation, Omega Centaurus, because early astronomers, before there were telescopes, actually thought that it was a star. I'm a little bit surprised at that, because I can certainly see, when I look at this object naked eye, no telescope at all, in a dark sky, so up at our, say at Heathcote, at our dark sky site there, you can definitely see that it's not a star, that it's a fuzzy blob.
Yeah, I would agree.
So quite how they ended up giving it a star designation, I'm not really sure, but well, they did.
So I think we'll move to the next object, which Noel has got up, and Caleb was actually mentioning Cat's Paw Nebula does look like a cat's paw, and it most certainly does look like a cat's paw. So that is the Cat's Paw Nebula. You can definitely make that out, that's for sure.
This is one of those rare objects where you can actually understand where the name comes from. Not a lot of those.
No. I'm going to agree with Caleb as well, where he says Statue of Liberty looks like Statue of Liberty.
Oh yeah, for sure, for sure. That's one of the obvious ones.
There's plenty of them, like Thor's helmet looks like Thor's helmet.
Hemsworth's helmet.
Yeah.
Hemsworth's helmet. Sorry, got that wrong. Hemsworth's helmet. That's right.
You know, I've always had trouble with the running chicken there.
Oh, that's shocking, that one.
So we're looking at Cat's Paw Nebula. What have we got on the Cat's Paw Nebula?
Yeah, so this is another example of an emission nebula. So now this image, this is a color image, so you can actually see some of the raw color shining through. And you can see that it's that real iconic sort of reddish, dullish, pinkish color coming through, and that is the light that's emitted by excited atomic hydrogen that makes up this cloud. So most of the mass, most of the visible mass in the universe is hydrogen. Around 75% of the atoms in the universe are hydrogen atoms. Then around 24% are helium, and then the rest is whatever else makes us up: carbon, hydrogen, carbon, oxygen, nitrogen, all of that. So this cloud is mostly atomic hydrogen. And this object, the Cat's Paw Nebula, is around 5,500 light years away. So again, far away, but pretty much our neighbor. And it's around 80 light years in diameter. So, a pretty darn large object. To give you some idea, the nearest star to our sun, Proxima Centauri, is 4 light years away. So that's a whole other star system, 4 light years away. And this object that we're looking at is 80 light years in diameter. So this is a really, really large, diffuse cloud of hydrogen. And most of these emission nebulae are stellar birthplaces. So they're regions of hydrogen gas that are collapsing under their own gravity and giving birth to new stars. And this particular object, the Cat's Paw Nebula, has given birth to around well, it contains tens of thousands of stars in it, and most of them are concealed sort of deep within the hydrogen gas. But this is actually a prime example of a really active region. So this Cat's Paw Nebula is sort of undergoing a baby boom, sort of creating a lot of new stars really, really rapidly. And when we look at this object with more sophisticated telescopes, those that we have in orbit, professional observatories, we can see that deep within this object, there are around 2,000 extremely young protoplanetary disks. So these are stars that have just been born and are just sort of starting to accumulate matter that will eventually evolve into planets themselves. So yeah, this is what you're looking at, is really the birthplace of stars.
So, Steve, do you have anything else to answer? To add to that?
I think Stefan's done a very thorough job on that.
He's leaving us for dead at the moment, isn't he? I've just been scrolling through the comments, and I've just noticed one from earlier on in the show, and we will get there in the end. But our Deep Sky section directors, I'm pretty sure it's his nephew, Paul Gardner, show me the jewel box. We will get to the jewel box, just for you, Paul. We will get there, and we will put it on for you, Paul, because we know how much you love it. So have we got another object ready to pop on the screen? I think we've lost Gerald. He's dropped off, which is not good. And I think Lee's still clouded out. And so
I've actually just started to uncloud, and I've got Triffid, which I think was on next.
Triffid was next on. So while Noel moves to Triffid as well, let's add Lee's in on Triffid there. Oh, yes, you can see that. Can we make that a bit bigger, Lee, by any chance? Oh, there we go. That's all right. Can we make the image a bit bigger? Is that possible?
Yeah. I'll go to 50%. Oh, too big.
Oh, that's a bit too big. If you can see some good detail in there, maybe 25%, hey? There we go. So you can get some good detail there. Now, can I just say, we were talking earlier about cost-effective astronomy equipment. Using the dodgy little 8-inch coffee grinder lead that I've got and my phone, I can image this object from my suburban backyard with my phone. All right, so that sort of should give you, and once Stefan and Steve start to talk to you about where this image is and how, like, it's not really that bright, really. When they start telling you a bit more about it, you'll understand that the fact that you can use a phone to image an object like this and get the color out of it is astonishing, especially from suburban Melbourne skies where I'm talking sort of 15 kilometers from the city. So it's quite amazing to have such basic equipment be able to do that. So take it away, guys.
A lot of the objects that we've been looking at tonight are in Scorpius. Not all of them, but a good proportion of them. What we've done now is we've actually just sort of popped over the border, fairly low in the east at the moment, into Sagittarius. So the Triffid Nebula is so named, as you can see there. It's divided into, well, kind of 3 lobes. I think there might actually be 4 if you look, but let's say 3. That dark nebula is Barnard 85, which sort of sits throughout the Triffid Nebula. If we had a colour image, part of the nebula is a red Emission Nebula, which Stefan's been talking about a fair bit. As we've seen other red nebula. There's also a blue part, which is a reflection nebula. Another interesting fact about the Triffid Nebula is that it's a baby. It's only about 300,000 years old. So an absolute baby in astronomical terms. It was created yesterday. It's about 5,200 light years away. So pretty close to us in the great scheme of things. Stefan, do you want to talk about other stuff to do with the Trifid?
Yeah, so I think you really covered most of it, but if you sort of look at the sort of dark Y shape in the center, that's the sort of absorption area. So that's a region of molecular gas that's very, very, very dense and is blocking the light from behind it. But just to the bottom of that Y, I'm not sure if you can zoom in on your screen. Yeah, if you can zoom in on that region there. Yeah, beautiful. So you can just about make it out. So at the bottom of that dark Y, on the left, there's this sort of hump. There's actually a really interesting region. You can just about resolve it in this scope. On the top of that hump, there's something that points out just up to the left. Yeah, you can just about see it just on the top of the hump.
Yes, yeah,
a little hard to see.
Right.
Yep.
Move your mouse down a touch. Up a little bit. I can just see. Yep, right there.
Yeah. So basically, just where his mouse is, there's actually this stellar jet that's emanating from this region. So this is caused by a new young star that's embedded really deep within this region, and it's emitting a lot of very, very high energy radiation that's actually blowing some of its some of the surrounding material out in this sort of really, really refined jet. Yeah, you can see it's a very, very narrow jet. You can just about make it out in this telescope. In space telescopes, you can see it very clearly. But this is a jet that's around almost a light year long. That's caused by outgassing from a very, very energetic young star. And
before you continue, Stefan, I'm going to just swap images. So we've got Lee's doing. What have you got on? What's your camera you've got on there, Lee? It's a monochromatic, isn't it? He's looking at his box.
Sorry, I just lost audio.
You lost audio. So you've got a monochromatic camera, right?
Yes. So that's a mono. That's actually with an infrared filter at the moment.
Infrared filter. Okay.
I'm only doing stacking at 30 seconds for those at the moment. So that's 6
you've got a
minutes
monochromatic. Worth. So Noel has been imaging this one in the background, which is
I've lost audio again. I think it's my batteries. Hang on.
So this is a live stack. So Noel, how many images is this?
We've got 11 stacks in there at the moment, and these are also 30-second stacks.
30 seconds. So we're talking 5.5 minutes worth of images right now.
Yeah.
Are you able to zoom in a bit? There we go. So Stefan, you can. I'm going to let you continue on now. Sorry, I just wanted to bring this color image up because this is a live stack color of Trifid. 5.5 minutes of color.
Beautiful.
Working on. And as amazing as Lee's image is, just to see this in color with the two opposing, the blue and the green, and the red, is unbelievable.
Yeah. So here you can really see what Steve was talking about earlier about the different regions of this nebula. So on the left, you see that that pinkish characteristic hydrogen emission nebula. And then on the right-hand side, you see that sort of faint blue glow. Now, that's not emitted light, that's reflected light. So this region, it's made up of slightly different gas, and instead of being excited and ionized, this is just light that's coming from stars and is being reflected off that nebula, and we're seeing it. So the Trifid Nebula is really a beautiful example of all three types of nebulae that I was talking about before. We've got emission in the pink, we've got reflection in the blue, and we've got absorption, which is the sort of dark parts that sort of sit in the middle, that dark Y that I was talking about. But yeah, as I was saying, as we were saying before, this is a really bright nebula, one of the jewels of the southern skies. Pointed right towards the middle of the Milky Way, and you really don't need the most sophisticated equipment to get a beautiful image of this target.
Are you saying my equipment's not sophisticated?
In its own way.
It's not.
I guess.
Steve, I was going to say, Steve, you got anything to add to that?
No, I think we've covered that one.
Yeah, we're all covered. Stefan, anything else before we move to our next object? Or
no, I think pretty much.
We're good to go. All right. So Noel is shifting across to M8 at the moment, so we'll watch him use. So what are you using here, Noel, when you're doing your tracking?
All right. So I'm using Sky Chart, or as the French would say, the Sky Chart, or Cartes.
Carte du ciel.
Yeah, that's the one. Yeah, thanks, guys.
Le Sky Chart.
So this is a planetarium software which I've got synchronized with my Skywatcher EQ6 mount. So that's using an ASCOM driver to talk to that anyway. So I'm using this to look up an object I want to go to, and I'm then instructing my telescope to move to it, and that's happened. And now over in SharpCap imaging, I'm going to clear this picture, and we'll just see what the first image comes through. I can do a process called plate solving in SharpCap, which will analyze the star patterns of the image and work out where it's actually imaging versus where it thinks it should be imaging, and then making corrections and move the telescope accordingly. Because I've been doing a few plate solving sequences already this evening, it's pretty well in sync. So this first, here we go. So that's lined up fairly well. I can run with that. I'll zoom out a bit. There we go. So that's the Lagoon Nebula coming through.
Oh, look at that. So how many? That's a 1/32 exposure.
Yeah, so that's two have come through now. So with more exposures, some of the noise in the background here will start to be filtered out, and some of the detail will become more prominent. And I haven't played with the stretching of the histogram yet, so I'll just leave that as it was for Triffid, because that's giving a fair bit of detail there already.
Beautiful. Now, Stefan, the time is for you to shine again. So we're on Lagoon Nebula. Take it away. It's all yours.
Just a couple of comments.
Go for it, Steve.
So this is the Lagoon Nebula, which is actually fairly close to M20, the Triffid Nebula in Sagittarius. It's another emission nebula, a really big one. In fact, it's one of allegedly only 2 star-forming regions that are visible to the naked eye in a dark sky. So there's the Lagoon Nebula, which is this one, and the Orion Nebula, which is the sword of Orion, or the handle of the pan, depending on which hemisphere you happen to be in. But this is, so M8 is a massive emission nebula. There's actually an embedded open cluster, which you can see there just above stars, just above the center, which is NGC 6530. And that helps to fluoresce the eastern side of the nebula. Did I say it's about 4,000 light years away? So a little bit closer than Triffid, but similar kind of distance. Stefan.
Yeah, so this is a really, really large emission nebulae. So it's around, you can see it's it's not quite circular, it's sort of almost rectangular shaped, right? You can see it's got one sort of much longer axis and then one much shorter axis. It really does sort of look almost rectangular. And the longest axis, it's around 100 light years across. the shorter axis around 40 light years across. So again, a really, really large region of gas and dust. And it's actually quite close to us, as Steve said. And because of this, it appears quite large in the sky. So what you're seeing here actually is about the same size as 3 full moons on the sky. So if the full moon was in that region, you would see that it would take about 3 full moons to cover that nebula. So it's quite actually a large thing. And just an interesting fact about this nebula itself, if you zoom in on the core, the really bright core in the middle, you'll see it's got this sort of pinkish blob right in the middle. Yeah, right deep in there. So this is a really, really active core in the Lagoon Nebula. A lot of star formation going on here. And actually, I'm not sure if our viewer is still here, who is asking about tornadoes in space, but this is actually an amazing example of a nebula that has a tornado in it. So deep in the core, not on a planet, but the actual nebula itself, there are certain winds that come from these stars embedded in the core, and these wind shears are causing some temperature gradients that are actually giving rise to some space tornadoes. And these tornadoes aren't like the tornadoes on Earth. They're incredibly large, almost half a light year across. Obviously, the telescopes that we have at the moment aren't really able to resolve these, but you can make out some of these space tornadoes in images from the Hubble Space Telescope. So a really beautiful, active, dynamic nebula, this one.
So we've got a question regarding the objects we've been looking at, obviously not related to the galaxies, just to the nebula and star clusters. But Shannon wants to know is, where are all these objects in relation to the Milky Way?
Yeah, so basically they're very close to us, right? They're only 4,000 light years away from Earth. And Earth itself is basically, if you think about the galaxy like a city with the CBD right in the middle, we're out in the suburbs. We're out on one of the spiral arms of our Milky Way galaxy, sort of 2/3 of the way from the center out to the edge. And most of these objects are pretty close to us, around 4,000, 5,000, 6,000 light years away. Whereas from us to the center of the galaxy is around, I think it's 15,000 light years, I want to say, something like that. Correct me if I'm wrong, Steve. I can't exactly remember.
So what you're saying essentially is these objects are Richmond, Fitzroy, Williamstown, Fitzroy, and we are Mornington Peninsula, Geelong.
Yeah, pretty much. That's probably a good estimate, I'd say.
Estimate, absolute estimate, but yeah.
I've got a beautiful app which shows exactly where, as you look objects up in the star charts, it's an app called Sky Safari, and it has a wonderful sort of galactic view of the Milky Way, which shows you in sort of 3 dimensions exactly where all the objects are. So yes, I can see looking at this one that it's fairly close to us. We actually sit in the what's called the Orion Spur, which is one of the arms fairly close to the center. But you know, as I think we mentioned earlier on, the Milky Way galaxy is about 100,000 light years across, and this is an object that's about 4,000 light years away. So it's in relatively near space to us.
So this is monochromatic. This is 8 1-minute images of Lagoon from Jen's warm house, as I'll call it.
I am nice and warm.
She is nice and warm in her roll-off observatory with her warm room. So this is obviously, you can see the difference between Jen's monochrome images and then Noel's. Oh, he's moved. From Noel's color to Jen's monochrome. and the different ways we can image objects.
So I quite like the monochromatic views, because this is kind of it's quite similar to what you would see through a telescope, just through the eyepiece. It wouldn't be quite as bright as this, but actually not that different. So I'm sort of more comfortable, as I tend to do mainly just visual astronomy rather than astrophotography. This is an image that I can sort of equate to, if you like.
So I'm going to, before we move to the next object, because we've been talking about cheap and expensive and what you can and can't do with objects, I would like to share something quickly just to show the folks at home with, once again, cheap equipment, what you can do with a phone. I will put a caveat on this and say that one of the astrophotographers from the ASV, Paul Milvain, processed this for me, but what you're about to see was taken with a phone camera attached to an 8-inch telescope in suburban Melbourne backyard. Can you see that? That is the Lagoon Nebula with a phone camera taken in suburban backyard. So if you've got a cheap telescope, cheap, a cheap go-to, or even, well, you need a tracking one, and you've got a phone and you can take raw data images with your phone, or you can get an app that can do that. This is what you can do with a phone. This is 40 15-second images, ISO 800, with a phone in, like I said, 15 kilometers from the city. So you can do this. It's not impossible. And while we're on Lagoon, Gerald's back, and we're going to have to go to his, because his is a live stack and it's absolutely stunning. So this is Lagoon, live stack from Geelong.
You can see it's a slightly different orientation from what
it is, yes, different orientation from what we've been looking at before.
You can see the open cluster was sort of above the bright patch in the other images, whereas it's off to the right in this. Beautiful.
Now, Janine is asking, how did I do that? As I said, so I have an 8-inch Meade go-to, and I have a $10 iPhone, or not iPhone, phone adapter that I bought off eBay, and I hook my phone onto that, and I use a program called Deep Sky Pro camera app. It's only on Android though at the moment, and it allows me to take raw data images, and I took a series of raw data images and I stacked them in AstroPixel processor, and then one of the astrophotography guys showed me how to process it. So that's how I did it. So I used that tracking telescope to track to Lagoon Nebula, and Lee, who's got his equipment running as well tonight, gave me a little Bluetooth clicker that I Bluetooth connect to my phone, and I click the Bluetooth clicker every 15 seconds. It's a very manual process, but that's what I can do with it, and that's what anyone can do with it. And there's a lot of people asking questions about it. We did do a live stream back in, Noel, when did we do our talk? It was April?
Yeah.
It was April.
Yep.
Yeah. So the April monthly meeting, which is on our YouTube page, Noel and I did a talk, and towards the end of that talk, I went through the processes that I go through for what I term astrophotography. So how you can do what I did in that image that you saw. It's a great way to get started, because I can't afford to spend lots of, thousands of dollars on fancy cameras and telescopes. And it's good fun. It's a lot of fun. It's a lot of manual labor, but it's a lot of fun. So, Lee. Let's go to Lee. Jump across to Lee. Lee, what have we got here?
Oh no, that was that's nothing at the moment. That was Lagoon.
Nothing at the moment. We'll come back to you. We'll go to Noel.
Yeah, the clouds have come back in, but I'm just getting ready for Paul Gardner's favourite.
Oh, okay. Now, just on that, it wasn't his nephew. Sorry,
It was
Jim.
him.
It was Jim. Jim, Paul told me to out you. He sent me a message and said to out you. So that was not his nephew. That was Jim, one of Paul's deep sky buddies. Actually, one of his mates. Now we are looking at Noel.
Yeah, the dragons of Ara. So it's visually, it's more one of the more challenging targets. I've seen it with the 40-inch at our dark sky site, but to photograph this one, it's quite a nice one when you do put a lot of time into getting some images of it, because you get the image of fighting dragons coming through quite clearly.
Now, Stefan, where is this in the night sky? And can we see it through a telescope, or do we need photography equipment to image it?
I think, as Noel suggested, he's glimpsed it in the 40-inch, but for typical visual equipment, which is sort of 8-10-inch telescope, you wouldn't be able to see these clouds, which are I think they're referred to as interstellar matter. So they're actually dust clouds, which are embedded in the Milky Way in the constellation Ara. So dragons of Ara. I haven't got a lot of. I was seeing if you could see this. You're supposed to be able to see a bit of a blue glow from off in the clouds, which is light that's reflected from some of the stars that are in the Milky Way in that area, and the light reflects off the dust clouds with a sort of a bluish glow. But I can't really see that, to be honest.
Yeah, it's sort of.
They make the
it's
whole
sort of
thing blue.
That's one way to do it. It sort of depends on the imaging filter that you're using, but really, because most of the atoms in the universe are hydrogen, really the dominant signal that we get from that is that sort of red pinkish emission. But when you're using what we call narrow band filters, you can isolate some of the emission from the blue region, which is emitted by atomic oxygen, and you can really highlight some of that blue. But in this, it's sort of swamped out by the really dominating hydrogen gas. So again, this region is an Emission Nebula. It's around 4,000 light years away.
So just quickly, Noel, how many minutes have you got there?
Yeah, only 8 minutes.
Okay,
So-
well, I'm just going to say it's not good enough, and I'm going to go for the 10 hours. So here's 10 hours.
10. Wow.
So this is Jen's image that she has spent 10 hours. She's taken 10 hours of data. Now, Jen, what is the composition of this? What have we got in this image?
This is taken with narrowband filters, with the HA and O3 and the S2 filters. 5-minute subs each with those.
So 10 hours worth at 5 minutes apiece.
Yeah.
Sorry, Noel, you lose this battle.
No,
That was also
surrender.
processed in Astro Pixel processor.
You can really see the dragons there, can't you?
You can absolutely see the dragons, yes. They're absolutely attacking each other at the moment.
That was one of my
that.
very first tries of a narrowband image, that one.
It's either that or it's a close-up of a T-Rex trying to, twiddle its thumbs together with an excellent.
Perhaps it's trying to eat a prawn.
It could be trying to eat a prawn. It's a T-Rex trying to hold on to a prawn, or it's two dragons fighting. Take your pick.
You can't find it though.
You can't find it.
It doesn't look enough like a prawn, apparently.
Right.
Now, Mark.
That's what 10 hours gets you. Like, so it's not just 10 hours of imaging, though, is it, Jen? It's 10 hours of images. But
yes.
There's setup time, pack down time between the images.
20 hours of processing.
Yep, 20 hours. So there's almost a week's worth of, well, not really a week. There's probably 2 full days worth of work in this by the time you're actually done with it.
Yeah. I'm still not happy with that yet.
No, okay. 10 hours and she's still not happy. So, Stefan, what were you going to say there?
Yeah, if I send a link to you in the chat, will you be able to bring up the photo that link
I
forwards you to?
can, yes, I can. And while we're waiting for, actually, he's going to do it right now, isn't he? Astrobin, here we go.
So
let me see what I can. Let me see what I can do. Hold on.
Sure.
All right, let me. You're asking a lot of me here. You're asking me to work technology out at 10:15 at night on a Friday. Windows. I want to share that one there. There we go. Yes, there you go.
So this is an image that I took of the same region, but what I want to highlight is actually down the bottom.
The egg.
So just out of the frame,
hang on,
down the bottom. So yeah, so this region is called the Fighting Dragons, and just below is what we call its egg. So this is actually the emissions from a very, very big, very, very bright star. So it's what we call an O-type star. It's around 40 solar masses. So it's 40 times the mass of our own sun, and it's nearing the end of its life, sort of throwing off some of its outer shells, forming this this really, really strange, intricate.
Can we see that? Zoom in.
Yeah, we can see that.
So
yeah, that
right
thing down there. And you can see this really prominent sort of outer faint oxygen shell, and then in the center that more defined bimodal, bipolar sort of emission. And so it's a really beautiful dynamic region.
Yeah, it's beautiful.
All right. We'll stop sharing that one now. And, we don't want to look at us, do we? We'll go back to that. Now, while Noel is moving across to Centaurus A, the hamburger, and while he does that, we're going to put Paul's favourite on, the jewel box.
Yeah, it's not. The only problem is it doesn't really pop in mono.
No, it's a lot better in colour.
Yeah, which is why I've actually got on my rig. I've got a DSLR, a Sony DSLR on the side, so I'm taking that at the same time.
Just hanging off the side. So for those of you who don't know, Lee has like the Frankenstein of astrophotography rig. He can pretty much hook anything onto it. In fact, I reckon he could hang the A-Team van off the side of his rig and still take images. But you can see the difference in colour in the stars there in this image.
Yeah.
I can. Do you want me to talk to this one?
Mm-hmm. While you do, if maybe Gerald or Jen can pop around to Jewel Box as well, see what they can bring up on it.
On the introductions, I think you mentioned, Mark, that I'm the coordinator of the Astronomy for the People section, which is our outreach program where we go off to schools and scout groups and community centres and things like that. Most of those viewing sessions that we do are in fairly light polluted skies, so they're in Melbourne suburbs. The Jewel Box is one of our favourite objects because it's visible in a very light polluted sky. It sits just off the edge of B Crux, which is the second brightest star in Crux, in the Southern Cross. And it's an open cluster. It's 6,400 light years away. And it has about 100 stars in it. You may not be able to see all of them there. And the stars are mainly blue giants. But there is actually a red supergiant, which unfortunately you can't see.
I can see it. It's there in the middle.
It's there, yeah.
It's there in the middle.
Do you see that sort of? That's an upside down capital A. So you can see it's sort of orange in the middle there. So that's a supergiant. The cluster itself is another baby. It's only about 7 million years old. So these are new stars that are burning themselves away quite rapidly. These blue giants and red supergiant. So this is we love this object in the AFTP because it's one that we can always see. You'd even be able to see this in from the centre of Melbourne, from the CBD.
So, just quickly to the team, any planetary nebula object imaging on the observation list? Ghost of Uranus was.
We had a couple.
Yeah, was on there. No one's moved to it yet. So if someone would like to pick up a planetary while we're
so the challenge is Noel is giving us a fairly wide field view. So we need someone that's got a narrow field view, I think we'll say, because planetary nebulae tend to be fairly small.
Yeah. So, Lee, I'm going to leave that one in your hands, and Jen as well. Actually, Jen's got Jewel Box. That's a monochrome image of Jewel Box. Sorry, Jen, but that's boring.
It is.
No colour. No colour. Hang on, what
No colour.
So that's not how we. So the Jewel Box is one of the.
There we go. We might have to mute. Who's got the noise in the background there? Who's got the wind blowing? Someone's
Not
got
me.
the
I'm nice and warm.
Yeah. That's the fan. It could be the
I'm going to mute Lee. It's Lee's fan that's blowing. Okay, so I think we're done on the Jewel Box. That's Gerald's. Oh, here we go. We're zooming in. Can we make that darker, Gerald? I know you can't hear me at the moment because. Oh, sorry. No, you can hear me, but you can't talk. Gerald's sound's gone. So
I can see the red supergiant.
The red, you can see the red supergiant. Yes,
of the capital A. There it's.
Yeah, it's right in the middle. Right in the middle there. It's the middle. It's the middle one in the A.
What we do with the kids when we're out at schools is we get them to look closely and tell us what kind of colours they can see, because there are a few different coloured stars, and we get obviously the orange colour of the red supergiant, the blue colours, the green colours, white colours as well. So the kids obviously they see the colours a lot better than we do. Their eyes let a little bit more light in than us old folk.
Speak for yourself, Steve. Speak for yourself.
Ian Somerville, who was...
Look at that. There we go. There you go.
Yeah, that's right. Ian
really
Somerville, who was the previous section director or coordinator of AFTP, could see a tartan star as well.
A tartan star. So that actually gives you a really good... Oh, gone the wrong way there, Gerald. That gives you a really good idea, though. You could really see that red star in the middle there. Even now, you can still see the difference in colour to the other stars. So we'll move across to Noel's screen now. We've got, for anyone who's hungry, if you're feeling a bit peckish, it's time for McDonald's or Hungry Jack's, a bit of a cheeseburger maybe. We'll go to the hamburger galaxy. And you can definitely make out the shape of a hamburger in that image. So you've got the bun on the top, the bun on the bottom, and the burger in the middle.
Another one of those objects where the name is actually quite nicely obvious.
It is very obvious. And now I want a cheeseburger. Take it away, guys. All yours. Some facts and some information on the hamburger galaxy, or Centaurus A.
Yeah, I guess I can kick it off. So this is another galaxy, so not an object that's within our Milky Way. It's very, very far off in the distance, around 10 to 15 million light years away. So very, very, very far away. And you can see this doesn't really look like the other galaxy that we were looking at, the southern pinwheel. It doesn't have any obvious sort of spiral structure. What you can actually see is this faint globular glow with this sort of intersecting beef patty, I guess you would call it. This sort of absorption, this dark lane that's passing through. And that's because this galaxy is actually an example of another galaxy that's undergone a merge in its past. So it's most likely a small spiral galaxy that's interacted with a much larger elliptical galaxy. And when they've collided and combined, they've formed this sort of really irregular galaxy. And so this is one of the brightest galaxies visible to us in our night sky. So it's a fantastic object to image. You can already see quite a lot of the structure coming out. Now this object, Centaurus A, is a really, really active galaxy. We know for a fact that there's a really large supermassive black hole at the core of this galaxy. Now, you can't see it in this image because we are imaging in optical wavelengths, in wavelengths of light that our eyes can see. But if you image this galaxy in the radio wavelengths and X-ray wavelengths, what you'll actually see are plumes emanating from the center, perpendicular to the dark lane. So you'll see these large plumes extending out to the northeast and southwest of the galaxy. And these plumes are created by the really, really high energy interaction of the supermassive black hole at the center of this galaxy with surrounding gas in that region. It's creating what are called relativistic jets. So these really high energy expulsions from the supermassive black hole at the middle. And some astrophysicists have made measurements of the supermassive black hole at the center of this galaxy, and they've actually measured the supermassive black hole to be around 55 million solar masses. So the same mass as 55 million suns in that single black hole. So this is a monster of an object. And yeah, it's accreting and devouring matter around it, some of the stars that are falling into it and blowing that energy out into these relativistic jets that we just can't really see. But some of these jets are literally millions of light years long, so spanning much further than the galaxy that we see.
Now, just quickly, we had someone earlier, and Noel, you might be able to answer this. Someone earlier asking about the blue lines or blue dots on the images. I can see now we've got a bit of a blue and a red there. Can you explain those?
Yeah, so these are hot pixels, or I guess faults in my camera's sensor, and usually you'll take a calibration frame which will subtract those from the image before it gets processed. I've just been lazy and not done that in this instance. So these are coming through as image faults. And normally, if you're processing them, doing like a big several-hour integration, they would be calibrated out, so they wouldn't appear in the final image. But yeah, most camera sensors do have some sort of level of faults to them. They're rarely perfect, so yeah, there's a process to eliminate those, but that's all that is. They're not a bright blue star or a bright red star, not to that level anyway.
There we go. You sounded a little bit like a Dalek there, Noel.
Let's talk about exterminating bright pixels.
Exterminate. Now, Lee said, hang on, I've got something. What have you got, Lee?
No. That's just it, right?
You're going, okay, well, we're just going to jump to Gerald's live stackaroonie. That's the best name for a... There we go. So this is Gerald's live stackaroonie of Hamburger Galaxy. Oh, there we go. There's the manual move of the camera. Can we sharpen that up at all, Gerald, for everyone? So this is a live stackaroonie.
That's good.
And I tell you what, that does look like a nicely brown piece of beef through the middle of that hamburger there. When you look at it in color like that. So this is another live color, like Noel's color image.
Juicy.
Hamburger. It does look juicy, doesn't it? Yes. So I like Shannon's version of it. It looks like a majestic taco. It's like one of those soft tacos that you can just fold in half. So we're moving to, Noel is moving to what is probably going to be our last object for the night, unless you've got something else, Jen.
I'm on the sombrero at the moment.
You're on sombrero.
Yeah, wait and see what comes up.
Kathleen Jackson wants to know, hopes it's vegetarian. It could be a vegetarian hamburger, I suppose. It could be. It could be a tofu burger or a shroom burger. It could be whatever we want. Well, so we got Jen's. That's not very. What's going on, Jen? Where's your image? Come on. Oh, we're 40 seconds away, 40 are we?
Seconds out.
Do we do a countdown?
I'm doing a countdown.
34 seconds away.
Come on, come on.
Like waiting for the kettle to boil, isn't it?
Or the burger to be cooked. Oh no, it's not.
Well, what have we got? We've got 8 seconds.
It's only
But,
120
Denise
seconds.
McMurray wants to know if anyone can image the Saturn Nebula before we go. But I will say my favourite is the Ghost of Jupiter. It's just not a good time of year for it, unfortunately. So can anyone get the Saturn Nebula at all? Lee, I'll throw that one your direction. We'll see what we can do, Denise.
The challenge with the Saturn Nebula is it's right down at the eastern horizon at the moment. It's only just pops up,
Popping up, yeah,
above the east, very low. So interestingly, it's actually very close to Saturn at the moment, right next door. So within a few degrees of Saturn. So,
it's not really planetary season at the moment, is it? Oh, look at this! Here we go. Sombrero Galaxy. Everyone get your hats on. We've gone from a taco to a sombrero.
Looks like a spaceship, isn't it?
It does look a little bit like a spaceship, yeah.
it's aliens. Ah! Don't tell Channel 7.
I've been cringing for the last 4 weeks when I've been watching those ads.
It's great. It's M104 Sombrero Galaxy.
So can I just say that this is what sombrero looks like when I look at sombrero through, well, maybe a little bit fainter than this. When I look at sombrero through the 8-inch I've got from the backyard in Melbourne here. So nowhere near as detailed as when she zooms in, obviously, but you can definitely see the line even in suburban Melbourne visually. Oh, here we go, guys. Challenge. Finish with Rofukio. Oh, sorry, Rofuki. Rofuki. I always get that one wrong. It's almost like when I call Mares mares, isn't it, Steve?
That only looks good in colour.
There you go. That
And
looks
the boring.
in colour. So that's a challenge for Noel and Gerald.
That's right.
Yeah. We'll see what we can do.
So isn't this is just your classic galaxy, isn't it, really? The edge-on spiral. It's such a great object to look at.
Anything about any information about it? What have we got on it? Stefan, got anything to add?
Off the top of my head, it's about 30 million light years away.
Yeah, so it is, so about 13 million light years away, yep. So this is another example of a spiral galaxy. So a galaxy like our own, but in contrast to the other spiral galaxy that we were looking at earlier, this isn't seen face on, this is seen edge on. So spiral galaxies are sort of like a disc, almost like a frisbee shape, right? So when we're seeing it face on, we see that beautiful spiral structure, but in this one, we're seeing it edge on. We're seeing just those dark lanes and the sort of halo of the extended core. Yeah, so again, it's about 10 million light years away. 10 million light years away. Yeah.
There we go.
It's part of the Virgo cluster, but sits a little bit further. Remember, we were looking earlier on at the if you like, the core of the cluster around Markarian's chain, and when we looked at M84 and M86 and M88, the big elliptical galaxies. This is part of the same cluster, but a little bit further, visually a little bit further away. Yeah, that's probably all I'll say.
That's all I've got to say.
I had a bit of a dried up moment there.
Jen, what have you got in your screen at the moment?
In my what, sorry?
What have you got? What are you imaging there? Oh no, that's your. We're looking at yours now. Oh, it's late. It's late. No, what have you got? What have we got here?
Well, there was a request for NGC. What is it? 4945. Yeah.
Yeah. There we go. How many images? What is this live stacked?
Yeah. Yep. So we've got 13 stacked now. 6.5 minutes worth coming through.
So what information have we got on this one, guys?
Yes. So just in broad, we'll focus in on the object. That in Centaurus there are 3 fantastic objects in Centaurus, 2 of which we've already looked at, which is Omega Centauri, which was the big globular cluster, Centaurus A, which was the lovely oddball galaxy, and then this third one, which is an edge-on spiral, NGC 4945. Similar sort of distance away, 13 million light years. A similar sort of brightness visually to Centaurus A as well. Sorry, Stefan, over to you.
No, yeah, there's not really much more I can add to this. It's another example of a spiral galaxy, but one that's viewed from us almost edge on, so you can't really see that spiral structure that clearly. But yeah, it's an example of a barred spiral galaxy. So the center has this sort of bar linearly stretching away from it. But yeah, there's not much more I can add. It's another beautiful close galaxy, around 11 million light years away, collection of billions of stars. But actually, also this galaxy is another example of one which has a very active nucleus. And we also suspect this galaxy of hosting a supermassive black hole in its center.
So you can see there, this is...
Sorry, go on.
I was just going to say, this is the color image version right here on Knowles, and then we have Lee's monochrome version of the same object.
This is one of the galaxies that I really like looking at this visually through the larger telescopes up at our dark site. It's one of the objects that you can see one of the galaxies that you can see a fair bit of detail in as well. So that those sort of what I call simplistically the sort of granularity in the galaxy, you can see that just through an eyepiece as well. It's a lovely object.
Wonderful. Now, we might sit in wonder and have a look at this for a moment. Actually, I was just going to see, we had a question if someone could maybe get Tarantula, but I don't know whether that's going to be... Gerald's already told me it's too low for him. I don't know if anyone else is able to get it.
It's too low for me, but I do have a stack from a few weeks ago.
Yeah, so's Gerald. Gerald's got a stack from a few weeks ago. So maybe we might close, unless Noel, you can't get it, can you?
I'm just going to have a look, but I think it's pretty low.
Yeah, we might end with we couldn't get Roafuki either. Too big to fit in GG's, so we'll call him GG's, the horsey's field of view, unless Lee, or you or Noel could fit it into your field of view.
Roafuki.
Yeah, Roho.
Rojo.
It's
Rojo.
huge. Yeah.
Yeah.
It is big, yeah.
If it's too big for, I mean, I could probably get it with the wide field camera maybe, but I don't know how it's going to look.
Did you want to give it a shot while we're mucking around with this sort of stuff? Oh, look at that. Some satellites going through there, Noel.
Yeah, got a couple.
I'll got rid of them.
Whoa. Got rid of them big time.
Sigma clipped their ears off.
Yeah. Where are you heading to, Noel?
I'm having a go at the tarantula, but I might get some street
there
light.
we go, Janine. We're trying the tarantula for you now. Doing our best. See what we can do. If we can't get it, we've got two guys who have got some images that they've put together of it from a few weeks back. But yeah, this time of night, this time of year, she's pretty low, isn't she?
Well, at the moment, it's just about as low as it goes in the southern sky.
Yeah.
It's just about reached the bottom of its sort of traverse around the south celestial pole.
See what we can do. Is that it there? Is it? No?
Well, I'm in the area.
Yeah, you're in the area. You can tell you're in the area.
For those who don't know, the Tarantula Nebula is an absolutely humongous nebula, and it's not in our galaxy. It actually sits inside the Large Magellanic Cloud.
I think we've got one of it. Gerald's come to the rescue. Well,
There it is. Look at that.
whoa. I don't know what I've done there.
So the Large Magellanic Cloud and the Small Magellanic Cloud are two small galaxies that are gravitationally attracted to the Milky Way galaxy and will eventually be probably absorbed into the Milky Way galaxy. Currently, the Large Magellanic Cloud is about 160,000 light years away. So this is a big object. The Tarantula Nebula that we're looking at here is a very, very big nebula. When you compare it with, in terms of how it looks visually, it's a similar kind of size to some of the other nebulae that we've been looking at. But it's sort of it's another zero on the end in terms of how many light years away it is. 160,000 light years. If the Tarantula Nebula were at the same distance as the Orion Nebula, it would probably cast shadows in the night. At night, it would be so bright in the sky.
I think probably would be definitely, wouldn't it?
Probably, definitely, yeah.
Yeah, probably, definitely. Anything else to add, Stefan?
Yeah, just one thing. So a lot of the stars that are in the core of the Tarantula Nebula, these are really massive, supermassive blue stars. And actually, a cool fact, one of the most luminous, so the most bright stars that we know of in the Milky Way or the near surroundings is actually embedded near the Tarantula Nebula. It's called R71. It's around 600,000 times brighter than our own sun. So, yeah.
Pretty dull then. Just before we pack it in, Noel, are you live stacking Tarantula now?
Yes. Yep. Just got it up.
Yeah. All right. Let's have a quick peek at that. This will be the end for the night. Unless Jen, you've got a live stack of it as well. But I think.
I'm on a Galaxy in Parvo.
Oh, you're on a Galaxy in Parvo. All right, we'll have a quick look at this, a quick peek at the Galaxy in Parvo, and I think we'll call it a night after this.
What's really good there, Mark, is
the colour.
Aside from the Tarantula Nebula, you can see that the Large Magellanic Cloud is just absolutely stuffed full of nebulae.
Yeah, to the right-hand side.
Fantastic object.
Yeah, and some little globs as well.
Yeah, it's amazing.
It's so hard to process that one. I still haven't had any success doing that one.
That little glob down the bottom.
No, that tarantula.
Oh, tarantula. Oh, I won't show you the one I did with the phone then. You'll yell at me.
I keep deleting it. I'm like, no.
So you can see a lot of activity there to the right-hand side as well. I think that's actually better like that. So what have we got? 3 stacks here. So this is what, a minute and a half?
Yeah.
No. Yeah, a minute and a half, isn't it?
Yeah.
Wonderful.
Sounds windy down there.
That's Lee's fan going to keep
that'll
him
be my
cool.
fan. Yeah, it's a bit warm in this room.
Right, so we'll have a little bit longer on this. We'll jump over to what Jen's got. What have you got again, Jen? You've got
a galaxy in Parvo.
What is it? Do we know what it is? What galaxy it is? You can't just say it's a galaxy in Parvo.
Yeah, I can. They call it NGC 6744.
There you go, NGC 6744. So this is Tarantula live stacked. We've got 2.5 minutes here at the moment. I'm impressed you got that one, Noel. It's considering how low it is at the moment.
Mm. Yeah, right over the neighbour's trees, I think.
Right. Now we'll just jump across to Jen quickly. And so this is it's a little spiral, isn't it?
Yeah, it's 7 minutes so far.
7 minutes. I don't know if you guys can make that out, but you can definitely see the arms on that. And yes, so while we're having a look at this, I don't know if Steve or Stefan have got any information on that at the moment.
Testing us a bit now. The Parvo, from a visual point of view, has 2 really good objects in it. One of them is a very bright globular cluster, which is NGC 6752, and the second object is this face-on galaxy, which is NGC 6744. I can probably, if I just click the right button here.
You're cheating, are you?
It's about 30 million light years away. Visual magnitude about +8.
So put that in perspective. That's light that we're looking at we're looking at light that's 30 million years old.
Yeah.
Yeah. So that kind of puts it in perspective. So what we're seeing here, so what was around 30 million years ago? I mean, dinosaurs weren't even around then, were they?
65 million years ago.
Yeah. So like it's a long time ago when you think about it.
So according to, I'm just looking up a bit of detail on this one. It's NGC 6744 is believed to be one of the most Milky Way-like of all the nearby spirals.
Oh, there you go.
It's got fluffy spiral arms and a large and distinctly elongated nucleus, says he, reading it from the text here.
It sounds like Elmo.
Do you have anything to add to that one, Stefan? Or
the other thing as well, you can't. If over to the, let's see if we can see it. There's actually a companion galaxy that is sort of like the Large Magellanic Cloud that sits off to one edge of it. I think it's. I could see just something down to the sort of the bottom. About where the arrow was before.
Yeah. That little fuzzy there. There's 3 little
it's
stars.
not very obvious, but there's a similar kind of a Magellanic Cloud kind of thing.
No. To your left-hand side there, Jen. Across to the left of it.
Yeah, just over a bit more there. Yeah.
Right there. Yep.
So that's the sort of Magellanic Cloud of NGC 6744.
Anything to add, Stefan?
Only that this. It's very similar in structure to the Milky Way, but it's actually a little bit bigger. Our Milky Way is something like 100,000 to 125,000 light years in diameter, but this one's a little bit larger, around 175,000 light years. So, it may look like a smudge on your screen, but really this thing is larger than our own galaxy.
It's a beast. Yeah, so I just want to thank everyone for coming along tonight. And some of you may have seen the banners scrolling across the bottom. Hoping lockdown ends when it does. We have a deep sky viewing session with some wonderful equipment going up to Shiraz Republic, sort of northeast of the dark sky site. Tickets are available through the link on our website or through the link on the Facebook page. It is a family-friendly event at Shiraz Republic. Dinner is included as part of the package with the drink as well. We will have some wonderful telescope equipment to look through up there. We also have, obviously, we have another bee astronomy event, our second one, which got, I guess, rescheduled because of COVID. It was meant to be on the 2nd of June, 2 nights ago, but we've rescheduled that to the 29th of June. That one comes cheese platter and a beer of glass. A glass of beer, not a beer of glass. Glass of beer. Tickets are on our website as well under the Bee Astronomy link. And for anyone who's not a member, a beer of glass. That's a good one.
How many beer of glasses have you had tonight?
Not many, I promise. For those who aren't members, if you want to become a member, asv.org.au/join. Typical standard membership, $75 plus a $20 joining fee. Residential memberships, 2 adults and however many kids under the age of 18, $130 including the joining fee. And we have a $55 junior membership, no joining fee for that as well. And we do have student and pensioner memberships as well. So asv.org.au/join. Like to thank everybody for coming along and watching us tonight and joining in. And we might pop back to just the scary faces of us and Jared's Tarantula Nebula. So thank you to Lee and Noel and Jen and Stefan and Steve and Gerald for his extremely live streamed astrophotography for coming along and helping out tonight. And we hope everybody enjoyed it. And we'll see you next time.
See you guys.
Thanks all.